Okay. My name is Katharina Rohlfink. It is really a pleasure to chair the last session for today. You probably have noticed that our schedule is quite tight because of the short presentation slots and short slots for the spotlights. Please allow me to ask you to be really on time for the keynotes and so on, because otherwise we will get into troubles. There is no space, you know, for this basically in the planning. At today's evening, this is my great pleasure to introduce Masako Myowa-Yamakoshi to you. She is now Professor of Development and Neuroscience at Kyoto University. 1999, she received her PhD from Kyoto University. She's the author of more than 400 publications, editorials, and books in primatology and developmental science. Her interest is the emergence and development of human social cognition and evolutionary foundation for it. And because this community is also about interdisciplinarity, she is just a great match to our interests in this respect as well. She pioneered comparative cognitive developmental science, integrating psychology, neuroscience, robotics, and biology to uncover both the shared and uniquely human aspects of the mind. Of a personal note, Masako wrote me that chimpanzees have been her teachers, but the dogs are her soulmates. We heard already today morning about some dogs, robotic and real, so we are looking very much forward to your talk. Thank you for coming.
Thank you. So, hello everyone. I know you may already feel satisfied with today's program and perhaps a little bit tired. I do too. But I hope you will stay with me just a bit longer. So, first of all, I would like to thank Katharina and all of the organizers of ICDL 2025 for giving me such a great opportunity to be here. So I'm Masako Myowa-Yamakoshi, the professor at Kyoto University in Japan. So today, I'm really happy to share with you some of the recent work from my lab. So I have no conflict of interest to disclosure. So first, let me briefly introduce myself. My research history over 30 years have been guided by this central question. Which characteristics of brain, cognition, and behavior are unique to human? That is evolutionary perspective. And second one, how do these phenotypes emerge and develop the ontogeny of human brain and cognition? And the last one is how and why does diversity in the human brain, cognition, and behavior emerge during development? I want to elucidate the principle of human development that account for its plastic trajectories. I began my research career by studying chimpanzees, investigating their brain and cognitive function, both in wild and captivity. Yep. So as a young researcher, I spent actually 2 years in the Republic of Guinea, observing wild chimpanzees. It was so beautiful day in my life. After the birth of my first child, my interest gradually shifted toward understanding the uniqueness of human brain and cognition. In our lab, we primarily study human participants, both here at Kyoto University and the Kyoto University Hospital. In recent years, our research has moved beyond the lab to include a natural, real-world setting. For example, from the evolutionary perspective, I have conducted comparative studies with chimpanzees to explore the biological foundation of human social cognition, focusing in particular on bodily imitation and action understanding. I would like to share one example from my research on chimpanzee cognition. As I was studying the imitative abilities of chimpanzees, I had a sudden realization. Perhaps humans and chimpanzees fundamentally attend to different aspects of others' action. To examine this idea, we used eye tracking technique to compare how human chimpanzees directed their attention when observing goal-directed action, performed by both humans and chimpanzees. It is important to note that all the chimpanzees in this study had been reared human environment, and they were already quite familiar with human environment and everyday objects such as cup, juice, and bottle. Okay, let's take a look at the result. Here you can see the attentional pattern of human 12-month-old infant. You may notice how infant gaze shift back and forth and again between the acted phase and manipulated object. Next is the chimpanzee scanning pattern. Okay, so here are the heat maps. Chimpanzees mainly track the movement of the object and rarely look at the actor's face. In contrast, human infants attend to both the actor's face and the object. So interestingly, we found the same pattern even when the actor was chimpanzees. So all right, today I would like to focus on two main things: the ontogeny of human social cognition and the principle of that underlying the diverse pathways of human development. So as you know, the trajectory of human development are remarkably diverse, extending far beyond the simple distinction between what we call typical and atypical. So my central aim to elucidate how and why such developmental diversity emerged. So from a life science perspective, I believe that 4 key concepts are particularly crucial in addressing this question: embodiment, interaction, dynamics, and sociality. So traditionally, the study of human development has been framed with the closed system model, like this. In this view, information is taken in from environment and processed internally and then expressed as output. But it is important to recognize that interacting with the environment does more than generate immediate outcomes. It also transforms the very mechanism that will shape future interaction. For this reason, I believe that adopting an open system perspective is essential if we truly understand the principle underlying the diversity of human development. This is my idea. So I'm very interested in applying the open system model to deepen our understanding of human development. So in this view, individuals are not static. They change continuously, shaped by their ongoing interaction with the environment. This influence is especially profound during the sensitive period of brain development, when external experience can leave lasting effect. So such interaction do more than shape immediate outcomes. They also reshape the mechanism that govern future interaction. This creates a reciprocal and dynamic developmental process, and importantly, this process involves not only infant, but also their caregivers. Both are influenced by their mutual exchanges, which in turn transform the very mechanism that guide subsequent development. So therefore, elucidating how human experiments these reciprocal dynamics with caregivers is very crucial. Then, what approaches can we use to visualize the dynamics of mother-infant interaction? So far, most studies have focused on describing brain-to-brain coupling between mother and infant. For example, one study in 2070 simultaneously measured the brain activity of both. The findings show that the adult direct gaze enhanced bidirectional neural coupling compared to an indirect gaze condition. Since then, research on brain coupling in mother-infant interaction has expanded rapidly, particularly in the context of social learning. Yet, it is important to recognize that much of this work remains limited scope. Many studies have looked only at the child side of the diet, limiting the mother's behavior in artificial ways, or reducing the analysis to simple average. However, as I mentioned, social interaction is by nature dynamic, reciprocal, and always evolving. So the question is, how can we truly capture the dynamics of human interaction from an open system perspective? Very difficult. But as a first step, we conceptualize the behavioral and physiological dynamics of dyadic interaction through the analogy with the spring mass model. From this model, we identify the three key properties of interaction dynamic. First, the homeostatic set point, the typical level to which each individual state converges over time. And second, the return strength or stability. This reflects the resilience to environmental perturbations. In other words, how quickly the system returns to its homeostatic point after being disturbed. And third one, the coupling effect. This captures the bidirectional dynamics that unfold between mother and infant across time. So far, studies of brain-to-brain synchronization in mother-infant interaction have mainly focused on this third property. On the other hand, the other two aspects, the homeostatic set point and the return strength or stability, have received comparatively little attention in study of human interaction. Yet, these factors may influence the coupling effect between partners and may help to explain both individual and dyadic variation in human interaction. So therefore, let's now turn to these two aspects. A fundamental fact is that all mammals, including humans, are constantly regulating their internal state in order to adapt to both internal and external changes in daily life. For example, homeostasis maintained balance by adapting to change, while allostasis maintained balance by predicting change before it happens. This regulatory process involves not only brain, but also the autonomic nervous system, hormonal and immune system, as well as the gut microbiota. Thus, to understand human development, we must consider not only how external stimuli are processed, but also how these multiple internal systems are regulated in an integrated way. This is my idea. So what is more important is that humans are deeply, very social animals. We survive not only by regulating our own internal state, but also by co-regulating with each other, but a process that is especially critical in infancy. Human infants are born unable to regulate their own internal balance and therefore rely entirely on their caregivers for survival. For this perspective, it becomes essential to examine the dynamics of co-regulation in mother-infant interaction. So one example of the biological system involved in both self-regulation and co-regulation of internal balance is the microbiota gut-brain axis. The recent studies in humans have shown that the microbiome is closely linked to not only physical disease, but also to mental health, such as depression and stress. Moreover, it is associated with general motivation, emotional regulation, and activation of the reward system. So now let's look at how these three properties come together in mother-infant interaction. So first, coupling effect. To capture the dynamics of mother-infant interaction, we measured not only brain activity using EEG, but also autonomic nervous system and the bodily movement with motion capture, all simultaneously. So we measured in such a setting. Here, the mother and the infant are simply playing together. Very cute. Yes. As you know, as you see, they are very multimodal interaction. So, sorry. So let's turn to the other two properties. So as indicators of the homeostatic set point, we measured each individual's gut microbiota and endocrine hormone and psychological and behavioral trait. As for the second property, return strength, we investigated mother-infant interaction using still face paradigm, very famous paradigm in psychology field. As the baseline, mother suddenly stops responding and keep a neutral face. For the infant, this is very strange and stressful situation, and it can also be stressful for the mother. Then, during the reunion phase, the mother resumes normal interaction. In other words, by introducing this stressor, we can artificially disrupt the synchronization between mother and infant, and then observe the system recovers. So to study the dynamic interaction in more natural setting, we developed a new software that used video to track their movement. In short, they combine the standard 2D motion tracking with video and depth data from the specialized cameras, enabling us to generate highly precisely pose of both mother and infant. Since time is limited today, I refer you to our 2024 publication for the technical detail. Please read this. But this is an example of what we are able to gain with this new technology. Here, I present a time series coherent metrics between the mother and infant hand movement. Interestingly, when the mother attempts to calm her crying infant, she also show subtle sign of panic, reflected in high jerk coherence. So next, let's focus on the infant side, examine the time series changing in both behavior and physiological response. As you can see, when exposed to the stressor, infants showed considerable individual differences in their reactions. For example, more than 30% of infants exhibited the typical pattern reported in previous still phase paradigm. They showed clear distress during the stressor and recovered promptly after reuniting with their mothers. Y-axis shows the distress, infant distress. By contrast, at a substantial proportion, or also over 30%, did not follow this recovery trajectory. Once their homeostatic balance was disrupted, they continued to display signs of distress even during the reunion phase. So these behavioral differences are also mirrored at the physiological level. Infants who struggled to recover from the stressor continued to show shortened RR interval, that is, elevated heart rate even during the reunion phase. So next, I will present the result on diet-neural coupling. In this analysis, we focused on the theta band and applied the weighted phase locking value. These results are based on the infant who were able to return to their homeostatic set point relatively quickly after the perturbation. And as you can see, brain-to-brain synchronization with the diet decreased during the stressor phase, and then recovered with the onset of the reunion phase. Next are the result of brain-to-brain synchronization between infants who continued to display distress even after the reunion phase and their mothers. Very interestingly, despite the persistence of behavioral signs of stress, the diet brain activity shows increased synchronization during the reunion phase, particularly in the frontal regions, similar to the pattern observed in typically recovering mother-infant pairs. Furthermore, we expanded our analysis to examine both interbody and brain synchrony within the diet. First, we looked at the EEG synchrony signals, like cross-correlation between the mother's and infant EEG, and identified the period of high brain synchrony, represent the red point like this. We then looked at the motion data during those same period. The results were very striking. During the free play, brain synchrony tended to precede movement. The mother hand often moved to closer to the infant after high brain synchrony. In contrast, during the reunion phase, mother's hand moved closer to the infant before high brain synchrony. This suggests that synchrony between brain and movement in the diet is flexible and context-dependent. As the next step, we need to uncover the mechanism underlying this phenomenon. Sorry. I'm sorry, my computer frozen. Okay. So, moreover, we have moved beyond the artificial lab setting to study mother-infant interaction in real-life context. This naturalistic neuroscience approach seeks to unite the precision of the lab with the complexity of the real world. In this study, we measure the autonomic nervous system physical activity, the gut microbiota, and emotional cognitive functioning of 78 Japanese mother-infant pairs followed continuously across 3 consecutive days. With the HeartNote device, a Holter ECG device developed by JSR Corporation. So with regard to the autonomic nervous system, we focused particularly on nighttime data to evaluate the baseline or set point of each individual autonomic nervous system activity. So specifically, we applied the time domain analysis, including the cardiac vagal index, CVI, and the cardiac sympathetic index, CSI. CVI reflects the parasympathetic activity, while CSI represents sympathetic activity. So now let's look at the result. First, I will present the finding on intra-individual interaction across multiple biological layers. Specifically, we examine the relationship among infant microbiome, their autonomic nervous system, and their emotional development as observed in everyday life. So over the past decade, research has shown that the microbiota matured gradually, reaching an adult-like and relatively stable between 3 and 4 years. However, most of these findings have come from the study of Western population, despite the substantial ethnic diversity in gut microbiota. So until recently, no studies have examined this process in Japanese infants. So since 2019, we have been building the large database on the gut microbiome and its relationship to physical and psychobehavioral traits in Japanese infants and their mothers. So to date, this database includes more than 4,000 mother-infant pairs. So our findings show that the Japanese gut microbiota develop in a very similar way to Western populations, but the process is slightly slower. So with this database, we examined the gut microbiota of Japanese infants in our study. The first, we looked at its relationship with the autonomic nervous system. We found that autonomic activity during sleep was closely linked to gut microbiota diversity. Specifically, infants with greater microbiota diversity showed higher vagal activity and lower sympathetic activity. So next, we examined the link between the autonomic nervous system and infant emotional cognitive functioning. We found that infants with higher vagal activity tended to show fewer negative emotion and less stress responses. Similarly, infants with higher vagal activity showed more positive emotional expression. So then, next, we looked at cross-layer interaction within the diet, with a focus on how maternal stress may influence the infant biology and behavior. So as mentioned earlier, the gut microbiota changed dramatically during the first 4 years of life. And what's important here is that these changes are not mainly driven by genetics. They are shaped much more by the environment afterwards, like diet, antibiotics, and lifestyle. So among these factors, one of the most powerful influences on microbiota development is the maternal condition, including the mode of feeding, delivery mode, skin contact, and lifestyle. In our study as well, we found that gut microbiota diversity was closely correlated between mother and their infant. This suggests that everyday co-regulation between caregiver and infant may also be reflected at the level of microbiota. So we then examined the inter-individual interaction between maternal stress and infant cognitive emotional development. The results were very clear. Infants of highly stressed mothers showed stronger negative emotional responses, lower level of self-regulation, and greater developmental risk, especially in executive functioning. Next, we focus on the inter-individual interaction between maternal stress and infant autonomic nervous system. We found that infants of highly stressed mothers show lower vagal activity, that is, reduced parasympathetic function. Importantly, no difference was observed in the sympathetic activity. So we also found that maternal stress was linked to infant gut microbiota seen not only in beta diversity, but also in 6 of the most prevalent microbiota. So let me summarize the result. First, we found strong correlation. First, we found a strong correlation between the gut microbiota and the cognitive behavior function of both mother and infant. Second, maternal stress was associated with infant cognitive risk, reduced vagal activity, and alteration in the microbiome composition. And third, maternal autonomic nervous system was linked to infant cognitive and behavioral development. By contrast, no linear correlation was observed between the autonomic nervous system of mother and infant. These findings suggest that alternative approach, such as nonlinear and This finding suggests that alternative approaches such as nonlinear physics-based analysis were required to uncover the dynamics of intra- and inter-individual interactions. So, as the next step, we visualize the circadian rhythm of 3 consecutive days of 24-hour autonomic nervous system recording. In collaboration with Professor Nagai, Yuki's laboratory, we used a recurrence plot to analyze how infants and mothers regulate each other's physiology. In addition, we tested whether maternal stress could be predicted using the self-organizing map model. The analysis revealed that maternal stress could be predicted from the autonomic nervous system activity of both mother and infant. So let's wrap up. Together, these findings enable us to establish a feedback loop model that provides a novel framework for understanding the dynamic processes of mother-infant co-regulation. So given the time limitation, I will focus on the 4 key premises of this model. Sorry. Okay. The first, co-regulation is essential for human development because infants cannot survive on their own and must rely on caregivers to regulate their physiology. And second, co-regulation is self-motivated. Caregivers are intrinsically motivated to engage in this process through repeated interaction with their infant. And third, co-regulation requires a physical pathway, never telepathic. For synchrony to occur between the internal state of caregivers and infant, an external channel such as touch, gaze, vocalization must be present. And finally, co-regulation is dynamic, continuous, and fallible. Because parents can never fully perceive their infant internal state, their responses are necessary. Lovely. Why? Please. Maybe I hope so. Okay. But not.
Does it not go further?
Okay. I will try. Yeah. So again, please come back to me. So third, the co-regulation required a physical pathway, never telepathic, for synchrony to occur between the internal state of caregiver and infant. And external channels such as touch, gaze, or vocalization must be present. Finally, co-regulation is dynamic and continuous and fallible. Because the parent can never fully perceive their infant internal state, their responses are necessarily imperfect and not always fully effective. So based on these four assumptions, we first propose the simplest model, like this, and then build it up step by step into a more complex and general one. For the full details, I'd be delighted if you could take a look at our recent papers. So building on this achievement, we are now developing the customized developmental support application tailored to the unique biological characteristic of each mother-infant pairs. So by advancing human science that truly connect with the real world and by creating fundamental but yet innovative tools that enrich the everyday lives of Homo sapiens, I aim to support the optimal developmental pathway of future generations, leading to lifelong physical and mental health. Thank you for your kind attention.
Thank you, Masako. Once more, this is always difficult to talk about stress and to feel it as well, right? Because we were late for the session and because of the technical problems, I hope it is okay to extend the session a little bit longer. Your questions, please. Yes, please.
Yes, thank you for your very interesting talk. I have one question concerning more the prevention aspect. Like in the future, do you think your work can also support some prevention program, for example? And I am thinking of one situation that has now a lot of attention, which is technoference. So, for example, some colleagues think that the still face paradigm can be mirroring also some situations where the parents are on the phone, for example, so this technoference situations. So I wanted to have your point of view on possible like prevention given your work. Thank you.
So I'm not non-native, so I'm afraid that full of your question can understand, but my aim to create a methodology to utilize for the prevention medicine. Before the mothers diagnosed the depression or stress, I want to catch the sign of the mother's physical or behavior, some kind of sign in their daily life, not in the hospital. This is our role, not a medical doctor, but a neuroscientist. We have to challenge to support their mental and physical health in their daily life.
Thank you very much for a fascinating talk. You have been talking about your studies of mother-infant pairs, but I wonder if the same results you could expect to find the same results with other types of caregivers, fathers, or other types, or even in cultures where the primary caregiver is actually a group of people.
Yes, I agree with you. If I have money, I want to do.
Hi, just really interesting talk. So I have two kind of questions that might be related. So firstly, you talk about kind of, the function of co-regulation is to maintain a homeostatic set point. In the context of the face-to-face interactions, like what is that set point? So what do you see that set point to be? What state do you want to be in during the course of a face-to-face interaction? And kind of relatedly, we're at ICDL, so in terms of kind of generative models, yes, so if you were to build a generative model that explains kind of some of the patterns of co-regulatory dynamics that you see, what would you put in it? So if the child is away from the set point, then the parent changes their behavior to bring the child back to the set point. But that wouldn't explain very much of the co-regulatory kind of dynamics that you're tracking in your thing. So what else would you put in that generative model other than that simple rule?
Yeah. I think that there are considerably very big cultural differences in terms of the mother-infant interaction. Maybe I think the Japanese mother not so much look at the baby's eye. Rather, they touch or vocalize without gaze exchanging. But as far as I observed your data, maybe European people, the interaction is very often use the eye gaze or eye contact during the interaction. Maybe this is the next challenge to confirm this point. It's okay.
I'd like to, well, first of all, thank you for the beautiful talk. I'd like to follow up on Sam's question, because so homeostasis means you're trying to move to one particular set point and really stay as close to it for as long as possible. And I think in many biological systems, that's maybe not the only thing we should be thinking about. There's also this notion of heterostasis, that maybe you want to keep certain variables also moving around a little bit and covering a certain distribution of values and make use of a certain dynamic range potentially. Couldn't it be the case that also in these settings, it's not about trying to go to one fixed point and stay there, but to really produce a certain level of variation across time?
Yes, I agree with you. Of course, the result today I show you is very limited condition, just an experimental situation or the 3 successive days condition. But if possible, I want to investigate it the whole day, for example, over 1 month or 1 year. I want to ask the participant to use a device, ECG device, and try to visualize their own physiological and behavioral changing in their own daily life. This is the next step. But we have to consider the ethics problem, very private matter.
All right.
Okay.
Thank you very much. Thank you once more for this wonderful talk, ending this wonderful first day, conference day.